webinar of the ISCAN Academy with the title Integration of Renewable Energy Sources in Power Systems. So, what is the agenda of this webinar? I will first present the characteristics of different renewable energy sources. Then I will go to the implementation of the RES into current electricity generation mix. I will go to grid challenges and impact of renewable energy sources, and then I will focus on ancillary services, today's approach and future solutions, and then I will come to a conclusion. So, as everybody knows, there are targets in Europe of the different member states for renewable energy sources, and the share of the renewable energy sources will increase very much in the next coming years. So it's more and more important in the European Union, but also in other countries, China, the US, Korea, the renewable energy sources. So what are the renewable energy sources? We can start. What is the sources of the primary energy? It's either the planetary motion, the geothermal energy, or the solar energy, so the energy from the sun. There are different processes, and for the planetary motion, the tidal process; for the solar energy, evaporation, rain, atmospheric circulation, wave movement, biomass production, and of course the irradiation from the sun. And then we can use it in for different kinds of renewable energy sources. Tidal power is not so common. There's only one power plant, as far as I know, in France. Geothermal power is used in some countries like Iceland and Japan for electricity generation. Hydropower is the most common source of renewables. Wind power is more and more important. Wave power plants, not so common. Then biomass production is more and more important in the world. In Germany, a lot of biogas plants are existing. And then from the sun, we have in some areas of the world concentrated solar plants and more PV photovoltaics. So renewable energy sources vary in their generation capability. First we see the wind. The wind speed vary during the year and during the day. Solar during the day. Only hydro is very easy to predict. So one example coming from Ireland for the variability from wind. We see the load curve, the system demand curve this curve, and we see the wind generation, and wind generation has on this Monday a peak with 42% of the overall electricity generation, whereas 18 hours before that there was only 2%, and this is a 1.2 gigawatt change in 18 hours. So the wind penetration can vary very much, and PV is often even worse. The predictable error of renewable energy sources is very important. Here, example, wind. Renewable energy sources as intermittent sources have to be predicted in order to implement a generation into the existing power system. However, every prediction has an inherent error. In general, the prediction error decreases with the geographical dispersion and with shorter time horizon. We see that with the years, the mean absolute error was decreasing, but is still important. This can be viewed on the diagram here. Today we have an error below 15% in 1 day before as a prediction horizon. So renewable energy sources are integrated at all voltage levels. Here we see a diagram of the system in Germany. Conventional power plants are connected to the transmission grid. So the very high voltage level with 220 or 380 kilovolt, and traditionally the power flow was to the high voltage level, which is 110 kilovolt, then the medium voltage 10 to 30 kilovolt, and then the low voltage system. Today, photovoltaic units are integrated mainly at the low voltage grid. The small roof systems or bigger voltage systems are in the medium voltage system, sometimes in the high voltage system. Wind is mainly connected to the medium high voltage system, and offshore wind is connected to the transmission system. Offshore wind power is, in my opinion, not a decentralized renewable energy source. Small biogas and combined heat power CHP units are connected mainly to the low voltage or medium voltage systems. And the increasing decentralized generation entails temporary reversal power flows. So we have a clear paradigm shift in the power generation at the distribution level. Historically, energy has been produced by bulk power plants situated at the transmission grid. Industry, households are connected to the distribution grid and demand energy. So there's a power flow from the TSO to the DSO. The situation today is that the energy generation at the distribution grid is gradually increasing, and that we have temporary reverse power flow from the households to the medium voltage system, and from the medium voltage system to high voltage and to the transmission level. The increasing fraction of total rated power makes the implementation more challenging. In many countries, like this example from Germany, the installed capacity of intermittent energy sources is significantly increasing. This entails an increasing number of days where renewable energies provide an important share to the energy. And here we see the development during the next years, and with the implementation and installation of new RES, and we have to cover with the energy mix the two extreme situation. It's the minimum demand of 35 gigawatt and the maximum demand of about 85 gigawatt. And this has to be covered in every second of the year. The increasing share of renewables has a clear impact on the grid challenges, and we will have we had in the last 10 years nearly a doubling of the renewable energies, and in the next years we have an annual growth rates of about 50 to 60%. Then the network operators facing major challenges due to the fast rise of the renewable energy sources. The main challenges is the fluctuating character of the wind and solar power, and it is necessary to balance between production and consumption. We will have major network expansion necessary due to the high amount of decentralized power plants. We need new information technologies in the network to control the fluctuating renewable energy sources, and a major challenge is to build up fully renewable power system for the economy like the European Union. We have frequency challenges in smaller power network with a high amount of renewable energy sources. So the more or the bigger the network is, the smaller these challenges are. The smaller the network is, like in Great Britain or Ireland, the less rotating mass and the less we have in this system the possibility to compensate the frequency changes. So we see on the right side the frequency behavior of the continental frequency control zone, where we have only frequencies between 50.05 and 49.95, so plus minus uh, 50 millihertz, whereas this fluctuation is much bigger in Great Britain. Especially with a high amount of fluctuating renewables, the variation in frequency increases. Due to that, wind turbines in Ireland are operated 5% under their maximum power to stabilize the network frequency. So what are the ancillary services? We can distinguish between the frequency control, the voltage control, the system management, and the grid restoration. So concerning frequency control, the network frequency has to be controlled. Retreating masses of the alternators and the turbines in the conventional power plants with their inertia are helping very much to, in the frequency control. We have a control reserve for balancing demand and supply. We have a control chain, primary, secondary, and tertiary control reserve. I come to that later. And this is provided by conventional power plants, as I have said. 50.2 hertz, I will come to that later. Voltage control, reactive power management is a key for the voltage control. Voltage support in case of a short circuit, and we have compensation systems with STATCOM, flexible AC transition systems, and so on. System management is monitoring and supervision in all network levels, network control unit as central controlling tool. We have congestion and feed-in management, especially for renewable energy sources, coordination of the network operation and prevention of asset overload. As the last ancillary service, we have grid restoration, switching measures for successive restoration of supply, formation of island grids, grid restoration after blackout, disconnection of disturbing sources, coordinated by central control unit and provided by power plants with that ability. Often storage, hydro and gas turbine power plants are used. Back to the frequency control. Here we have the frequency in the frequency control zone continental Europe with the very small tolerance band. And what are causes for imbalance? We have stochastic deviation, loss of plants, prediction error. Deterministic deviation reasons is the design of the market. All plants and loads change their power at the same time. And we see the principle, if we have generation and load in a balance, we have exactly 50 hertz, the nominal frequency in the network, and if we have more load, we have lower frequency, and if we have too much generation, we have higher frequency. To help or to keep the frequency in the target area, we have the control reserve. First, the primary control reserve, which is seen here, provided by conventional power plants, which are able to change their power within the demanded time frame. So within 5 to seconds, 5 to 30 seconds, we can have the call of all necessary primary control reserve. This is done in each conventional power plant by a controller, so that we have really a decentralized activation. Because this controller in the power plant is measuring the frequency and activating for example, the steam valve of the turbine. The secondary control reserve is provided mostly conventional power plants, fast start gas turbines and hydroelectric power plants, storage and pump storage. Here we have a centralized activation via signal from the load frequency control, and the tertiary control reserve is provided by conventional power plants as well as partially renewable energies like biomass and CHPs, and is automatic activation by TSOs. What issues are raised by wind in the European Union concerning the provision of control reserve, displacement of conventional generation and ancillary service providers? We have manageable renewable energy sources which may participate in load frequency control and the influence of voltage control during high production situation. Concerning the primary control, the challenges are very high. The action of speed regulators from the generation units responding to changes in the system frequency, and this is not influenced by wind power except capacity grid. Secondary control, it's an automatic action of the generation responding to changes in the system frequency. It's only slightly affected by wind generation ramps when opposite to system demand. Presently, no need to contact further bands. The tertiary control manual power variation has to be provided in less than 15 minutes. It's only slightly affected by wind generation ramps when opposite to system demand. And then we have now running reserves and hot reserves, and this has a significant influence of wind power. Reserve provisions must be increased due to wind power forecast errors. Reserves are checked from the day before until real time. I'm coming to the voltage control in case of inverse power flow, especially in the low voltage grid. In the past, we had always a power flow from the medium voltage via the transformer in the power station and the distribution line to the loads. We see here in the sketch 2 households, and along the distribution line we have a voltage fall, and we have provide according the voltage quality norm in Europe or in the world, voltage band plus minus 10%. In this case, we see that in the red case that we have at the end of the distribution line less than 207 volt, so this is not allowed. So we have to change the voltage ratio between medium and low voltage level in the transformer. This can be done when the transformer is switched off, and then an employee of the DSO can change this by hand. We call this offload tape changer. In this time, the households are switched off. Of course, this can't be done in regular manner, only one time in 5 years. We must find other solutions. The alternative is, in the case we have reverse power flow, we have a maximum infeed of photovoltaics via this inverter, and then in this case, in the time of the day where we have no load and maximum infeed or minimum load, we have power flow from the households to the power station and to the medium voltage grid, and then the voltage fall is just in the other direction. And in this case, we have an overvoltage case, which is also not allowed. In this case, the inverter has to switch off, but this is not a solution. So what can we do? We can either have a stronger line, so more copper, a second line to the households to reduce the voltage fall, or we can have via reactive power an inductive behavior of the voltage of the PV system, and with that we can reduce the voltage here, so that we keep inside the plus 10% line. In the transmission grid, we have sometimes the need for capacitive behavior of the generation because of this nose curve. We see here the feed-in of reactive power. In the case we have a power flow over a line of some gigawatts, And we see that in the blue curve that we have to provide, or if we don't provide enough capacitive power, we can have a collapse of the voltage here at a little more than 2 gigawatt over the transmission line. And only including feed-in of reactive power, we can increase the stability limit by nearly 1 gigawatt, and this has to be done by capacitive power from a power plant at the end of this power line. This is, for example, very important for the transmission of all the power from North Germany to South Germany, from the wind power plants in North Germany. We have to provide capacitive reactive power in South Germany. What can be sources of this reactive power? Of course, conventional power plants. In Germany, we have the special case that one synchronous generator, one synchronous alternator in an atomic, in a nuclear power plant, which is not working anymore, was used. So only the alternator is operated and the complete steam cycle the operation is stopped. And with this synchronous generator, we provide now the reactive power needed by the transmission grid. But this can be also done by the renewable energy sources in the distribution grid, so that they operate in a flexible manner as a flexible reactive power compensation system. Only in the low voltage system we need the reactive power for voltage control, as I have described before. The additional advantage of this generator is that it provides rotating masses. The challenge is that we can only provide this reactive power from the decentralized renewable energy sources by ICT, by information control technologies. Concerning system management, we have congestion and feed-in management. We have to monitor the current network storage status. We have continuous monitoring at all voltage levels, but today this is mainly in the high voltage and in the medium voltage. At the low voltage grids, there's not this visibility, which can be only improved by smart meters in the future. Congestion management is to prevent local assets overloads, for example, by feed-in management. This is is for renewables. For conventional power plants, we call it redispatch or other actions to influence the feed-in. like counter trading. Securing and providing ancillary services, frequency control, voltage control, and grid restoration. The responsibilities of the TSOs, the transmission system operators, is organization of the use of control, reserve, and reactive power, congestion management, and grid restoration. And the responsibility of the DSOs, local voltage control and grid restoration, supportive for the TSO. Generation management and feed-in management. We can have a curtailment of the renewable energy sources. The more the share of the renewables is, the more we have this curtailment. So we have here in black the must-run units. We have in green the renewable energy sources, and we have in brown remaining classical units that take part in the market, and we have the load curve, and if we have too much renewable energy sources, we need this curtailment, so that renewable energy sources production must be limited to balance demand and generation. Grid restoration in case of a blackout. The current concept after a blackout incorporates grid restoration via the transmission network level, power plants with start-up ability, hydro and gas turbine power plants build up the supply of the maximum voltage level. Thereby they help other plants in the island to restart, and separate island networks are synchronized to bigger grid systems. Lower network levels and loads are gradually connected. It is important that the renewable energy sources are integrated into this grid restoration plan and can be controlled also in a case of a blackout. Of course, frequent trainings of the restoration process should be done. So I come to the vision for the future. Ancillary service need to be provided by area power plants. So the old world was a central world. We had the conventional central power plants, which were only providing the energy and the ancillary service to the transmission system operators, and the energy and the ancillary service were then transported or were transferred also to the distribution system operator and then to the consumers. The new world is a decentralized world where we have decentralized renewable power sources, and these are feeding into the distribution system at all levels, and we have only a small conventional generation with only small contribution to the energy and the ancillary services, so that the ancillary services have to be provided by the area power plant. So we have a clear power flow from the DSO to the DSO, and also a flow of the ancillary services. As a conclusion, we can state that modern renewable energy sources with inverter systems are suitable for the provision of ancillary services. So the frequency control can be provided in the distribution and the transmission network. The frequency stabilization with wind power can be done like in Ireland or by PV systems. The question is how different renewable energy sources can be pooled to a control reserve pool which can contribute to the markets. Concerning voltage control, we have an active reactive power management with inverter systems without active feed-in, for example a phase shift mode with inverter systems that is like the example of the generation system in this former nuclear power plant. We can have reactive power of a solar PV plant at night and also providing reactive power from a wind farm at no wind. There will be new control mechanisms in the future for voltage control in the distribution system. For example, a voltage control depending on the actual voltage at the connection point. And system management and grid restoration in case of a blackout. Distribution networks like 110 kilovolt network catch themselves in an island network under the support of renewable generators, free dispatch, feed-in and congestion management in some hours instead of network expansion. And controlled induction of smart meters with, of course, a bagatelle limit of some kilowatts because very small units are too expensive concerning the smart meters. Okay, I'm now at the end of my presentation. I thank very much the contribution of the University of Milano, Politecnico di Milano, and I thank also my colleagues from the University of Braunschweig for their contribution, and thank you for your participation in this webinar. Thank you very much.